Welcome to all of you. As I told you in the previous class that we will discuss problems related to equivalence relation. So I am here with a problem related to equivalence relation. I hope everyone has understood all the concepts related to the relations and types of relation with the help of examples. Now I am starting this question. This question is based on the equivalence relation. We have to check whether the given relation satisfy all three conditions of reflexive, symmetric and transitive. So all of you please see the video very carefully. Question is, check whether the relation r equal to xy such that x minus y is a multiple of 2. There is a relation between x and y such that x minus y is a multiple of 2. That is, x minus y is an even number. We have to check whether this relation is equivalence or not. First of all, we write like this: r is equal to xy such that x minus y equal to 2q. Since it is a multiple of 2 where q can be any integers, it may be positive, it may be negative also. Now after this, there are three conditions here: reflexive, symmetric and transitive. First of all, we go with step by step. First is reflexive. We know that reflexive means mapping to itself. That is, we write like the relation like r is equal to xx. Here we have xy. Now we have done the mapping to itself. So it becomes xx such that x minus x is equal to 2q. Now this relation holds true because x minus x equal to 0 and 0 is a multiple of 2. So when the mapping is done to itself, we get the relation here 0 is a multiple of 2. That is true. So this relation is reflexive. Now for the symmetric case, we know that if A and B are related, B and A must be related to that relation. So what we are doing here, the relation is x minus y equal to 2q. For symmetric, what I have written, yx such that y minus x is a multiple of 2, which is also true because if 8 minus 4 equal to 4, multiple of 2, then 4 minus 8 is also minus 4. It is also a multiple of 2 because they are integers. 2 can divide 4, 2 can divide minus 4 also. We are not taking only positive numbers here, we are taking negative also. So this relation also holds true because if x and y are the terms such that x minus y is a multiple of 2, y minus x must be a multiple of 2, whether it comes in the negative form. Then this relation holds symmetric. Now for the last transitive, what I am going to take another number. Like here we have x and y, I have taken yz such that y minus z is equal to 2q, that is multiple of 2. Now from these two relations, what I can make for transitive, x and z, since y are in common in both, so x and z such that x minus z equal to 2q. Now this relation also holds true because suppose 8 minus 4 which is equal to 4, multiple of 2, 4 minus 2 which is equal to 2, multiple of 2. Then when we add both 8 minus 4 plus 4 minus 2, 4 and 4 cancel out. 8 minus 2 becomes 6. It is also a multiple of 2. So I have written like this also: 8 minus 4, 4, multiple of 2, 4 minus 2, 2, multiple of 2, 4 and 4 cancel out, 8 minus 2, 6. That is, the relation comes between x and z. So this relation holds transitive also. So finally, the relation shows the reflexiveness, symmetricness and transitiveness. Any relation that satisfies all three criteria, all three conditions, is considered to be an equivalence relation. I will show you one more example to make your concept clear and tough. Next problem related to equivalence relation is, let A is a set containing the element from 1 to 9 and R be a relation which is defined in A cross A, that is the Cartesian product of A and A, defined by AB related to CD. Here we have the relation of A and B with C and D. So the relation is A plus D is equal to B plus C. that is the first term and the last term and the middle two terms for A, B and C D in A cross A. We have to prove that this relation is an equivalence relation. We have the elements A, B related to C, D with a relation A plus D is equal to B plus C. Now we will prove that this relation is an equivalence relation. For that equivalence relation, we need to prove three things: reflexiveness, symmetricness and transitiveness. First I am going to start with reflexiveness. First of all, I have written the relation A and B related to C and D such that A plus D equal to B plus C. Now for the reflexiveness, the mapping should be done to itself. That is, for reflexiveness, let A be related to AB only. So what will be the relation become from this? First and the last term and the middle two terms, like this. The first and the last term A and B and A. A plus B gives equal to B plus A, which is obviously correct because this property shows the commutative property. A plus B equal to B plus A, which is everywhere true for all the numbers, for all the number related to this set. So A plus B equal to B plus A shows that this relation is reflexive in nature. Okay, now for symmetric, what we are going to do, if the relation is given between A, B and CD, we will shift it. CD related to AB, that is, let CD related to AB such that the first and the last term C plus B and the middle two terms D and A. C plus B equal to D plus A. This result and the given result are same. Just the position of the terms are shifted. The LHS becomes the RHS and the RHS becomes the LHS. That is, they have the same meaning because they also show the property of addition here. 4 plus 3 and 3 plus 4 gives the same result. That is, this relation holds symmetric also. So mapping to itself is proved. Inverse property is proved, that is reflexiveness and symmetricness. Third one, for transitive, what I am going to take, the relation is given between AB and CD. I will take the relation between CD and EF. CD related to EF such that C plus F, the first and the last, and the middle two, D plus E. Let this term be the first equation. Given equation, we already have A plus D equal to B plus C. Subtracting both the terms, both the like terms, we can say A plus D minus D plus E, B plus C minus C plus F. By solving, we get A minus E equal to B minus F. Shifting the negative values to the left and the right, we get A plus F equal to B plus E. Now this will give us the property that A plus F and B plus E, that is first and the last and the middle two. So the relation becomes AB and EF, first and the last and the middle two. So AB and CD are related, CD and EF are related, CD and CD are common. So the relation becomes AB and EF. That is the property of transitive also proved here. So all three criteria are fulfilled by the relation, hence this relation is also equivalence relation. This is a very important question. This question has came into the board exam also. So please go through this question very carefully. And in every question of equivalence relation, what you need to do, you have to prove three conditions: mapping to itself, reflexive, inverse relation, and the third relation, that is transitiveness, in order to prove that equivalency. In the next part of the video, I will show you what is equivalence class. The next topic related to equivalence relation is equivalence class. The meaning of equivalence class can be defined as that particular set of the given set which satisfy the condition of equivalence relation. That is, the class of all members of a set, all those elements of the set that satisfy the conditions of equivalence relation. For example, if we have a set A containing the element 1 to 10 and a relation AB related to CD such that A plus D equal to B plus C, just proved in the previous question. Find equivalence class of 3, 4. Here A, B, C, D all belong to set A. We have to find the equivalence class of 3, 4 if R is a equivalence relation. Now equivalence class of 3, 4 means the other pair that satisfy the relation equivalent with respect to 3, 4. I am again telling you that equivalence class is that class of members that satisfy the condition of equivalence relation. So as per this relation, let 3, 4 related to AB on A cross A, where A is defined as 1 to 10. Now from this relation I am using 3 plus B, A plus D we have, B plus C, so 3 plus B equal to 4 plus A. Now in order to satisfy this equation, the value of A may be 1 and the value of B may be 2. Then this become 5, this also become 5. This is one pair. As many pairs as we can take using this set. So the other pairs are 2, 3, because if we put 2 here we get 6, 3 here, this is also 6, 3, 4, 7, 7, 4, 5, 8, 8, and similarly we can take all the pairs. So the equivalence class of 3, 4 are these pairs which will help this set, this element set to become equivalence. So when we take the relation between 3, 4 and 1, 2, it is equivalence. When we take the relation between 3, 4 and 2, 3, it is equivalence. So equivalence class are the class of all such members that will help to prove a relation as equivalence. I hope you all understand all the topics related to relations. Now try solving as many questions of equivalence relation and equivalence class. In the next video, I will tell you about the concept related to functions. Thank you very much.